In this video, we begin looking at section 3.7, which is basically tangent lines to implicitly defined functions. So I'm going to break this topic into two bits. I first want to focus on just the idea of an implicit function itself, okay? And then the next video will be about the calculus part of taking derivatives, okay? So let's just compare for a second on two sides, right? Something that looks like y is equal to f of x, right? And for that, for example, you could have like, y is equal to x squared minus 5, or y is equal to sine of x, or y is equal to the arc sine of x, or y is equal to e to the 3x squared plus 5. All of these functions have something in common, that on the left-hand side there is a y, and on the right-hand side there is a quote formula that involves just a single variable x. Okay? And these are the kind of functions we're used to. So for example, this problem, you can create an x and a y column, right? And because y is a function of x, you can choose values of x that you want. And then the y value you just get by plugging in the x value. To get -4, when you plug in 0, you get -5, -1, you'll get -4, -3, -3 squared is 9, 9 minus 5 is 4. So and all these functions work the same way when they are what's called explicitly defined. That means that y is explicitly given as a formula that involves x. So with an explicit function, you can have x in this column, y equal f of x in the other column, and you pick 1, you'll get f of 1 for the y value. You pick -5, you'll get some function evaluated at -5 for the y value. Okay, so those are the kind of functions we're used to working with. Okay, compare that to, for example, what's called an implicitly defined function. Implicit function on the other side, and let's look at an example of one. Okay, an example of one would be x multiplied by y, x multiplied by y plus x plus y is equal to 5. And now you notice in this example that on the left-hand side we have a formula that mixes x's and y's together. And on this side, it just so happens that the right-hand side is equal to a constant, right? So an implicitly defined function is just a more complicated expression that has x's and y's mixed together, okay? That's one example. You could also have, for example, x squared y plus y cubed is equal to cosine of xy. Right? Again, what we're seeing here is that we're just seeing formulas on the left-hand side that has both x's and y's in it. And in this particular formula, you can have a right-hand side that involves x's and y's. Okay? So these are, an implicitly defined function is where at this level, that where the right and left-hand side involves some functions, mixture of formulas that have x's and y's in them. Okay, so if we take a look at, for example, specifically x times y plus x plus y equal to 5, and you try to create some values for x and y, one has to deal with these formula, the x and y's, together at the same time. For example, if you pick x is equal to 0, right, then you look back into this equation and you put x is equal to 0, which will lead to 0 plus y is equal to 5, which implies that you've figured out what y is equal to. So now you can say that when x is 0, y had to be equal to 5. Okay, and when x is equal to 1, for example, now you get y plus 1 plus y is equal to 5. And now you can see that you actually have to work to figure out what y is. 2y plus 1 is equal to 5. 2y is equal to 4. Y is equal to 2. Okay? So when x is equal to 1, and you plug into this implicitly defined function, you have some more work to do to solve for y. Okay? So now we can say that when x is equal to 1, y is equal to 2. So we can erase the work if you prefer. And now just replace this with y is equal to 2. See, it's not as straightforward implicitly defined functions as explicit, where if you have a formula for y as a function of x, you pick an x and plug into the formula and you immediately get y. You have to do some work with implicitly defined functions. So perhaps when x is equal to 3, you will get 3y plus 3 plus y is equal to 5. You'll find that 4y is equal to 2. You'll find that y is equal to a half. Right? So now when x is equal to 3, you can say that y was equal to a half. Okay. All right. And that's how you would create maybe a table of values for this implicitly defined function. Okay. And then if you plot enough of those xy points, okay, and ask your calculator to graph them. Not all calculators can do this, but the software I use called Mathematica can plot these. Here is a plot of this implicitly defined function. You can see that it looks like it's got two little pieces to it. So look, that when x is 0, we found that y was equal to 5, correct? Right here on the right-hand side of the screen. Right here. Okay, and that we can see from the picture. When x is equal to 0 on the horizontal axis, y is equal to 5 right there. That's that little dot right there. And when x is equal to 1, right down here we can see on the x-axis, we can see a x value of 1, read it up to the graph, and you can see that the y value, reading it across to the left, is equal to 2. So this, I'm not sure if you can see my mouse, but when x is 1, read it across to the y-axis, y is 2. And that's what we were seeing here. Okay, sorry, let me go back to the screen. And when x is 3, y was supposed to be a half, so let's look at x is equal to 3, read it up to the graph. We can see that reading it across to the left, you'll get a half for the y value. Okay, so putting all the xy values together will create this graph that has two pieces. Okay, so that's an example of an implicitly defined function. Okay, let's look at implicitly defined functions have some really interesting looking graphs. Let's look at x squared times y plus y cubed equal to the cosine of x times y. Oh boy. And there is a plot of this, okay, that's actually a complicated looking plot. Now let's plot this on a smaller range. Let's plot from x is equal to -1 to 1, y is equal to -1 to 1. Maybe the plot won't look so weird. Okay. Oh, double equals. Sorry, y'all, I gotta learn to. My calculator was plotting the wrong thing there. Okay, now let's plot from, say, -6 to 6. Okay, and you'll see what all the points that satisfy that equation look like. Okay, so it's this little kind of hump-shaped graph. So if we plot this from, say, -6 to 6, and let's plot this from y going from 0 to 2, there is the graph of this function. Okay, so let's see if we can test one point on this function. Add a page below. Okay, so if you just look at the graph of x squared y plus y cubed, x squared times y plus y cubed equal to the cosine of xy. Alright, so let's take a look at this. What happens when x is equal to 0? Could you find a y value? Okay, well, when x is equal to 0, you get 0 squared times y plus y cubed is equal to the cosine of 0 times y. So we're going to try to figure out what equation we have to solve. Y cubed will equal to the cosine of 0 is equal to 1, which implies that y had to be positive 1. So when x is equal to 0, y is equal to 1. And that's what we're seeing right here on this graph. When x is 0, y is a value of 1. Okay? So, and then other values of x, the computer would have plotted them for you. Okay? So that is an introduction to the implicitly defined functions. The question that we're going to need to ask ourselves next is, perhaps, what is an equation of the tangent line to the function f of x, or to the implicitly defined function, to the implicit function at a specific value of xy? That is the question we'll ask in the next video.